Good afternoon, everyone. We're Team 15 from Singapore International School. I'm Doris, and here with me, we have So Bin, whose favorite toy, also our best friend, is a polar bear. Over there on the other end, we have Jasper, who's drinking a cup of iced milk tea, and in the middle, we have Michael, who's putting on sunscreen while we're indoors. Anyway, looking at what they have with them, they all share one thing in common. These are all made possible by hydrogen bonds. In fact, hydrogen bonds are everywhere in our daily lives.
So now we'll demonstrate how hydrogen bonds are formed. In this analogy, I represent an oxygen atom with two hydrogen atoms, Doris and Michael. The three of us together form a water molecule like this. So in this analogy, each chocolate bar represents a pair of electrons, with the shared chocolate bar representing the two electrons that form covalent bonds between oxygen and hydrogen. So I have 4 chocolate bars, and 2 of them are for sharing with Doris and Michael.
So Bin is more electronegative, which means that she's able to grab to a larger portion of the chocolate bar. Meanwhile, Michael and I are only able to grab to such a small portion. So Bin, you have quite a lot to eat, right? You're pretty full. But Michael and I were always hungry. Michael, 你肚餓嗰時會點啊？
我食多啲嘢咯。大家可以見到嘅係 Jasper 同兩位觀眾分享咗2條 chocolate bars， 形成一個水分子。而佢自己都有2條多咗嘅 chocolate bars。肚餓嘅我咧，被 Jasper 大量嘅 chocolate bars 所吸引，特別係佢未同任何人分享嘅嗰2條。
唔該晒 Michael 嘅解釋，兩位觀眾可以翻去坐啦。電負性係量度原子吸引電子嘅能力。喺頭先示範裏面，我同蘇斌嘅電負性係高過其他人。喺一個 covalent bond 裏面，電負性高啲嘅原子就有大有部分負電荷，而電負性低啲嘅原子就有部分正電荷。就好似頭先咁咯，喺個 covalent bond 裏面，我同我哋嘅電負性高啲嘅原子就有更強嘅吸引力，所以咧就會拉嗰對共用原子近啲自己。就好似喺頭先咁樣，我同蘇斌永遠都想拉條朱力條近啲自己，因為嗰個朱力條係代表嗰對共用電子。咁 Michael， 我想問下你啦，咁係咪咩都可以形成 hydrogen bond 㗎？
咁就唔啱咯喎。其實咧 ，hydrogen bond 係一個好特別嘅分子間作用嚟，唔係所有分子都可以形成 hydrogen bond 嘅。其實咧，只有 nitrogen、oxygen 同 fluorine 呢3種好中意電子嘅原子先可以形成 hydrogen bond。所以咧 ，hydrogen bond 其實係一個好強嘅分子間作用嚟。
Indeed, the presence of hydrogen bond is responsible for many unique properties in life science. Now, we're going to talk about the importance of hydrogen bonds in soap bubbles.
In these 2 beakers, we have the same quantity of dry ice and water. Pouring water over the dry ice causes the dry ice to spline quickly and release fumes of carbon dioxide that help to blow the bubble. Doris, on the right, smear a little soap over the beaker lid, and Sobin, who's closer to me, smear a little soap with glycerol. The rising fumes of carbon dioxide is pushing against the little soap, causing the bubbles to form.
So, what is this experiment about? I'm sure many of you play around with soap bubbles when we were children, but have you ever wondered why the soap bubbles always pop after a while? Well, let's take a closer look at the diagram. As water solution is evaporated due to evaporation, this causes the soap film to thin and create holes within the soap solution.
So when glycerol is added into the solution, it forms hydrogen bonds with water as it dissolves. So now we can see that on the surface of the soap film, there are some glycerol molecules, while there are less water molecules. This means that the rate of water evaporation is slower. Also, glycerol is a humectant, which means that it's able to attract water from its surroundings. All these properties make glycerol bubbles last longer. Over to you, Michael.
In fact, the bubble without glycerol pop first most of the time. But however, due to experimental errors, we were not able to produce the accurate results this time. We can discuss about this during the Q&A section.
Okay, guys, so why is this property important? Well, this property of glycerol makes glycerol useful as a moisturizing agent in cosmetic products such as cream and soap, or as an anti-drying medium in products such as toothpaste. In food, this property makes glycerol useful as it can increase the water content and preserve food.
Yeah, all this talk about sunscreen makes me want to exercise. And when we exercise, we sweat, right? Something kind of similar happens to plants. So plants lose water due to evaporation. When we sweat, we want to drink water, right? But for plants, they actually pull up water from the roots. And this process is called the transpiration pull.
Okay, so the setup we have here is called a potometer, which can be used to measure the rate of water uptake in plants. So what we have here are two leafy shoots of equal mass, and they're inserted into sealed flask. So one flask contains soapy water, while the other contains deionized water.
Before we started the experiment, the meniscus of water in the capillary tubes was set to the 15 cm mark. Now we can see that the water level is at approximately 11.5 for the pure water, and it is at around 13 cm for the soapy water setup, showing that water has been absorbed by the plants, but at different rates.
Thanks for the detailed explanation by Michael. So, as water is drawn from the xylem, a continuous column of water is being pulled up. Why? Let's take a closer look at a diagram showing what is happening inside the leaf. Water is lost from the mesophyll cells due to evaporation. This causes the water potential in the cells to drop, and water molecules are drawn from the nearby xylem vessels which have a higher water potential.
That's right, Jasper. And hydrogen bonding is extremely important in this process. It makes sure that the water molecules are together, which means that they can be pulled up in one continuous chain from the roots to the leaves without being broken down into sections.
Okay, then why do you think the rate of water uptake in the potometer with soap slower, Doris?
Is it because it interrupts the hydrogen bonding?
That's correct. Soap interrupts the hydrogen bonds in water. Soap has one hydrophobic end, which hates water molecules, and one hydrophilic end, which loves water molecules. So the soap molecules try to push themselves all the way to the water surface of the water to stick their hydrophobic ends out of the water.
That's right. So throughout the soap solutions, the soap molecules keep disrupting the formation of hydrogen bonds. That's why it is harder for the plant to pull out the whole chain. So the rate of water uptake is slower in the soapy water than that in the pure water setup. But Sopen, why is this important?
Okay, let me explain using an example. Do you know that Californian redwoods can grow over 100 meters tall? Wait, 100 meters? That's equivalent to 55 microns stacked on top of each other.
Whoa.
So how is this possible? Well, hydrogen bonds allow water and plants to be transported over long distances in a continuous column. Therefore, without hydrogen bonds, plants would probably be only able to grow to a few centimeters tall. Wait, that's just like Doris.
Why? Anyway, 而家我哋會用中文解釋一下 hydrogen bond 點樣影響冰嘅結構。如果我哋將一粒冰抌落杯水度會點呢？係啦，佢會浮嘅，大家都知啦。咁如果我哋將粒雪成固體嘅油抌落杯油度呢，佢會沉嘅喎。其實呢個現象會發生喺大部分其他嘅物質身上。當一個物質凝固嘅時候，分子嘅動能就會減少，而分子之間嘅排列就會變密，並排成一個秩序有規則嘅結構。咁所以呢，佢嘅體積就會下降，而佢密度就會上升啦。咁 Jasper 點解冰會浮啊？
等我解釋俾大家聽下啦。冰之所以浮喺水面，係因為當水結冰嗰時，一個井然有序六角形結構就開始形成。咁樣呢個特性令到固態水比液態水佔用更加多嘅空間，所以冰嘅密度比水低。咁你可能會問啦，冰浮係一日，唔浮係一日，點解我哋咁在意呢？
咁其實咧，呢啲白色嘅冰帽就反射咗85%嘅陽光啦。如果冇咗佢哋嘅話咧，我哋地球就真係好熱㗎啦。同埋浮冰亦都為北極熊啊、企鵝啊、海象啊呢啲極地動物提供咗重要嘅棲息地。如果冇咗佢哋嘅話咧，我哋就見唔到呢啲可愛嘅動物㗎啦。仲有啊，浮冰喺極地地區形成好重要嘅熱絕緣作用，佢確保嗰度嘅水溫咧係適合海洋生物生存嘅。
Okay, so from bubbles to plants to polar bears, hydrogen bonds are the nameless hero behind that make many phenomena in the life sciences possible. Without hydrogen bonds, life on Earth would likely not exist as we know. Thank you.